In this problem, we are looking for an equivalent inductance of two inductors that include mutual inductance. Important concepts we'll need include that of mutual inductance, the fact that the inductor voltage is the sum of the self-induced and mutually induced voltages, and Kirchhoff's voltage law. Now let's review the information from the problem statement. We are asked to find an expression for the equivalent inductance for the circuit shown below. So we're looking for the equivalent inductance looking into the terminal pair. So we can imagine that somehow these pair of inductors can look like a single inductor, L sub EQ. Now, to give us a common point of reference here, I will define the voltage and current associated with the equivalent inductance, and then use that same voltage and current on the given circuit. As always, make sure that you use the passive reference configuration when you define voltage and current like this. We can then write that the voltage is related to the inductor current as the time rate of change of current times the equivalent inductance. Now over here, we observe that we've got an individual voltage that appears across each inductance. So what I'll do is make specific labels to keep track of the individual voltage and individual current for each inductor. So for example, we know on the top inductor that the voltage is L1 times di1 dt. Now the mutual inductance essentially says that the current flowing through the other inductor induces a second voltage, which is given by M times di2 dt. In a similar fashion, the voltage that appears across L2 is given by the self-inductance term, L2 times di2 dt, plus the mutual inductance times the derivative of current in the other inductor. You have to be a little careful on handling signs when you do this. Use plus when the current I2 enters that dotted terminal. So it's pretty easy to do provided that you keep the direction straight. Now let's see how Kirchhoff's voltage law comes in handy. I'm going to make a closed path starting at the lower left, and I first bump into the negative sign, so I'll write that as minus V. I then encounter the positive sign, so I'll write plus V1, and again bumping into the second positive sign, we've got plus V2. That equals 0. And I'll bring the voltage on the other side. Now we can see that since these elements are connected in series, that the current I1 and I2 are the same, and they in fact equal the current I. We can then take these expressions for V and I, put those back into that defining equation for voltage, and then identify the equivalent inductance in terms of L1, L2, and M. Alright, let's move on to the details of our solution process. I'll begin by jotting down definitions for the voltage and current associated with each inductor, taking great care to use passive reference configuration throughout. Now the current I1 is the same thing as the current I2, which is the same as this current I. now I can apply Kirchhoff's voltage law and write an expression for this common voltage V. So I write minus V plus V1 plus V2 equals 0. Let's get that subscript where we need it. I'll bring the voltage on the other side. V1 plus V2 equals V. Now this entire situation we are trying to say can be expressed as a single equivalent inductance L sub EQ. This voltage then is the sum of those individual voltages V1 and V2. Now, V1 is given by the sum of two terms. The first one is the self-induced voltage, which would be L1 times dI1 dt. Then we add in the voltage induced by the magnetic coupling between those two inductors. So that would be M times dI2 dt. Again, I use the plus here because I2 enters the dotted terminal. If it would have been entering the opposite terminal, we would have written down a negative sign instead. In a similar fashion, V2 is the sum of the induced or the self-induced voltage, L2 times dI2 dt, plus the voltage coupled in from the other inductor by way of the magnetic field. So it would be M times dI, actually dI1 dt. Now what do we do next? Come back here for a moment. Recall that I1 and I2 are equal to each other, and they're actually equal to I. So I'm going to drop the subscripts. And the sum of the two voltages is that voltage V associated with our equivalent inductance. So I'm going to add these two equations together. And that says that V1 plus V2 is V equals this conglomeration of four elements. Now each one, or each term, has dI dt common. So I'll pull out all of the coefficients. And again, observe the linkages back here. So it looks like LEQ must be L1 plus L2 plus 2 times M. And that's the result to part A. Now part B is very, very similar, of course, but not exactly the same. We're going to move the dot to the bottom terminal. I'm going to go ahead and reverse my polarity for V2 and also change the direction of I2. Again, I want to maintain passive reference configuration and also have I2 pointing into the terminal. Since I changed my direction of I2, then we need to write that I1 is minus I2. Also, if we do Kirchhoff's voltage law again, we see that everything is the same except now we bump into the negative sign first. And that gives us V1 minus V2 equals V. Let me go ahead and put these subscripts back in. And that's our situation for V1. Here we see I2 entering the dotted terminal, so that part is the same. Here I1 enters the dotted terminal, so everything stays the same over there. Now a critical difference that we need to observe is that we have a different sign on I2. So when I remove all of the subscripts, I also need to change out the sign. And I would take care of that here as well. Also, we write that V is V1 minus V2. I then subtract these two equations. Minus a minus gives us a plus. And here we have minus M. And now it appears that the equivalent inductance is L1 plus L2 minus 2M. So in part B, we see that changing the dot means that we get an equivalent inductance that's smaller than the original configuration. So what do we do? In summary, we wrote each inductor voltage as the sum of self-induced and mutually induced voltages. We then recognized that the series-connected inductors shared the same current. We then applied KVL to write the overall voltage in terms of the two inductor voltages, and then substitute and rewrote in the form V equals L di1 dt in order to identify the equivalent inductance. That wraps it up for this problem.